Look around you. Stop for just a moment and truly observe the world you inhabit. The screen before your eyes operates on principles of quantum mechanics. The chair supporting you resists gravity through electromagnetic forces between atoms. The air filling your lungs contains precisely the right mixture of gases to sustain complex life. Your heart beats roughly once per second, pumping blood through a network of vessels that, if laid end to end, would circle the Earth twice over. Now pull back further. Your planet orbits a medium-sized star at exactly the right distance to maintain liquid water on its surface. Your solar system sits in a quiet arm of a spiral galaxy, far enough from the violent core to avoid sterilizing radiation, yet close enough to benefit from heavy elements forged in ancient supernovae. Your universe operates according to mathematical laws so precise, so finely calibrated, that even the tiniest deviation would render existence impossible. This is not an accident. Or is it? The question of cosmic fine-tuning represents one of the most profound mysteries in modern science. We have discovered that the universe operates on a razor's edge of possibility, balanced so precariously that the alteration of a single fundamental constant by even one part in a billion billion would collapse the entire edifice of reality. The electromagnetic force that holds atoms together, the strong nuclear force binding protons and neutrons, the precise mass of the electron, the exact rate of cosmic expansion, all of these appear calibrated with impossible precision. Some interpret this as evidence of purpose, of deliberate design by an intelligence beyond comprehension. Others argue that we simply exist in the one universe among countless others that happen to get the numbers right, that our observations are biased by the simple fact that we could only evolve in a universe capable of supporting our existence. Still, others suggest that our understanding remains incomplete, that deeper principles await discovery that will explain why the universe must be exactly as we observe it. But before we can evaluate these competing explanations, we must first understand exactly how improbable our universe truly is. We must examine the knife edge upon which all of existence balances. We must confront the staggering precision required for stars to burn, atoms to form, and consciousness to emerge. Let us begin with something deceptively simple, the force that holds you to the earth beneath your feet. Gravity is the weakest of nature's fundamental forces, and yet it shapes the largest structures in the cosmos. Every galaxy, every star, every planet exists because gravity can overcome the thermal pressure that would otherwise scatter matter across infinite space. But gravity's strength is not arbitrary. The gravitational constant, denoted by physicists as g, determines how strongly mass attracts mass across distance. If gravity were significantly stronger, the consequences would unfold rapidly and catastrophically. Stars would form more easily from collapsing gas clouds, but they would also burn through their nuclear fuel at accelerated rates. A star like our Sun, which has burned steadily for nearly 5 billion years and will continue for 5 billion more, might exhaust its hydrogen fuel in mere millions of years under stronger gravity. Complex life requires billions of years to evolve. Even simple single-celled organisms needed roughly 1 billion years to emerge on Earth. Intelligent, technological civilizations require even longer timescales. But the problem extends deeper than mere stellar lifespans. If gravity were too strong, the stars themselves would be dramatically different. The mass required to ignite nuclear fusion in a stellar core would decrease, meaning smaller stars would become possible. This might sound beneficial, but it creates a fundamental issue. Smaller stars burn hotter and more intensely relative to their mass. The stable, long-lived stars that provide steady illumination for orbiting planets would be replaced by violent, short-lived furnaces. Increase gravity by a factor of just a few thousand, and the universe would contain nothing but miniature stars that live for perhaps a few million years at most. These stars would be so small, so dense, that the planets orbiting them would need to huddle impossibly close to receive adequate warmth. But at such proximity, tidal forces would wreak havoc, potentially locking planets in synchronous rotation so that one hemisphere permanently faces the star while the other freezes in eternal darkness. Even if life could somehow emerge in the narrow twilight zone between these extremes, it would have scant time to evolve before its parent star exploded or collapsed. Conversely, if gravity were weaker, different but equally insurmountable problems would arise. Weaken gravity by a similar factor, and stars might never form at all. The primordial gas clouds that filled the early universe would lack sufficient attractive force to overcome their internal pressure and collapse into fusion-igniting spheres. Without stars, there would be no nuclear furnaces to forge the heavy elements necessary for chemistry, for planets, for life. The universe would remain a cold, diffuse fog of hydrogen and helium, forever dark, forever sterile. Even modest weakening of gravity would extend stellar lifespans to incomprehensible durations. But this apparent benefit masks a deeper issue. Longer-lived stars burn cooler and dimmer. A star might persist for trillions of years, but it would emit so little energy that planets would need to orbit at knife-edge distances to maintain temperatures compatible with liquid water. The habitable zone, that narrow band around a star where conditions permit life, would shrink to a razor-thin ring, making planetary formation in the right location exponentially less likely. But gravity does not act alone. It interacts intimately with another fundamental force: electromagnetism. The electromagnetic force governs the behavior of charged particles. It binds electrons to atomic nuclei, creating the atoms that form molecules, that form cells, that form bodies, that form civilizations. Electromagnetism is vastly stronger than gravity, roughly 10 to the power of 36 times stronger. In fact, this enormous disparity might seem arbitrary, but it proves essential for the existence of stable matter. If electromagnetism were stronger relative to gravity, atoms would contract. Electrons would orbit more tightly around nuclei, reducing atomic radii. This might appear inconsequential, but chemistry depends critically on atomic size. Chemical bonds form when electron clouds overlap in specific ways, creating stable molecular structures. Shrink atoms too much, and chemistry as we know it becomes impossible. The proteins that catalyze biological reactions, the DNA molecules that store genetic information, the lipid membranes that separate cells from their environment, all of these depend on atoms having precisely the sizes they do. Furthermore, stronger electromagnetism would affect the behavior of electrons in metals, potentially eliminating the conductive properties that make electrical technology possible. The very neurons firing in your brain rely on the movement of charged ions across cell membranes, a process calibrated to the actual strength of electromagnetic forces. Alter that strength significantly, and neural signaling might become impossible, rendering consciousness itself unattainable. Weaken electromagnetism, and atoms grow larger, more diffuse. Chemical bonds become weaker, less stable. Complex molecules fall apart more easily under thermal agitation. The precise molecular machinery of life, which operates at the edge of thermal noise even in our universe, would be impossible to maintain. DNA would unravel too easily to store genetic information reliably. Proteins would denature at lower temperatures, preventing the evolution of warm-blooded organisms. Life might be restricted to the coldest environments, where thermal motion remains minimal, but such environments also slow chemical reactions, potentially preventing evolution altogether. The relationship between gravity and electromagnetism also determines the existence and properties of planets. Planets form from the accretion of dust and gas in protoplanetary disks around young stars. Electromagnetic forces bind atoms into molecules, molecules into dust grains into pebbles, pebbles into planetesimals. Gravity takes over at larger scales, pulling planetesimals together into planets. This handoff from electromagnetic to gravitational dominance occurs at a specific size scale determined by the ratio between these forces. Alter this ratio, and planets might form too easily or not at all. They might be too small to retain atmospheres, or so large that crushing gravity prevents the development of surface conditions compatible with life. Earth's mass, its iron core generating a protective magnetic field, its plate tectonics recycling carbon and regulating climate over geological timescales. All of these depend on our planet forming within a narrow range of sizes, which in turn depends on the precise balance between gravity and electromagnetism. Yet even with the right strength of gravity and electromagnetism, matter itself requires another force to exist: the strong nuclear force. Inside every atomic nucleus, protons cluster together despite their mutual electromagnetic repulsion. Protons carry positive electric charge, and like charges, repel with a force that increases dramatically as distance decreases. At the tiny scales inside a nucleus, this electromagnetic repulsion becomes powerful enough to blast nuclei apart. That it does not is due entirely to the strong nuclear force, which binds protons and neutrons together with even greater strength at very short range. The strong force is approximately 100 times stronger than electromagnetism, but only over distances comparable to the size of a nucleus, roughly 1 femtometer, or 1/4,000,000th of a meter. Beyond this range, the strong force drops to zero with extraordinary rapidity. This precise strength and range prove absolutely critical for the existence of stable matter. If the strong force were slightly weaker, atomic nuclei would disintegrate. Even a reduction of just a few percent would prevent the formation of deuterium, the isotope of hydrogen containing 1 proton and 1 neutron. Without deuterium, the nuclear fusion reactions that power stars would halt at hydrogen. Stars could still form and burn, but only through the slow proton-proton chain reaction that barely functions in our own sunday. More massive stars, which rely on the CNO cycle incorporating carbon, nitrogen, and oxygen as catalysts, would be impossible. These stars synthesize the heavy elements scattered by supernova explosions. The carbon in your cells, the oxygen you breathe, the iron in your blood. Without them, the universe would contain only hydrogen and helium. Forever. But the situation worsens. If the strong force were weaker still, even ordinary hydrogen nuclei single protons might become unstable. The proton might decay, its quarks rearranging into other particles, leaving behind a universe filled only with electrons, neutrinos, and photons. No atoms, no chemistry, no possibility of complexity. Strengthen the strong force, and different catastrophes unfold. A slightly stronger strong force would allow 2 protons to bind together without the need for an intervening neutron, creating a form of helium-2 that is unstable in our universe. This might seem beneficial, making fusion easier and stars more readily formed. But the consequences cascade through nuclear physics in destructive ways. If 2 protons can bind easily, then the primordial universe, hot, dense, and filled with energetic collisions, would have fused all of its hydrogen into helium and heavier elements within minutes of the Big Bang. No hydrogen would remain. This is catastrophic for several reasons. First, stars require hydrogen fuel. Without it, stellar evolution as we know it becomes impossible. Second, hydrogen is the simplest element, the foundation of chemistry. Water is H2O. Methane is CH4. The amino acids forming proteins contain chains of carbon atoms festooned with hydrogen. Remove hydrogen from the periodic table, and you remove the basis for organic chemistry entirely. Moreover, a strong force might permit the existence of stable diprotons, which would alter the energy landscape of nuclear reactions. Stars might burn through heavier elements too quickly, or not burn them at all, depending on the complex interplay of binding energies. The delicate nucleosynthesis occurring in stellar cores and supernovae, which produces the precise mixture of elements we observe in the universe, would be disrupted beyond recognition. But nuclear physics involves yet another force, one more subtle, but equally essential: the weak nuclear force. The weak force governs radioactive decay and certain nuclear reactions. It is responsible for beta decay, where neutrons transform into protons, or vice versa, emitting electrons or positrons in the process. This force is far weaker than the strong nuclear force or electromagnetism, yet it plays an indispensable role in stellar nucleosynthesis and the evolution of the universe. Inside stars, the weak force enables the primary fusion reaction that powers stars like our Sunday protons collide and occasionally fuse, with the weak force converting 1 proton into a neutron, creating deuterium. This reaction proceeds very slowly. A proton in the sun's core waits billions of years, on average, before undergoing fusion. This glacial pace is precisely what allows stars to burn steadily for billions of years, rather than exploding immediately. Strengthen the weak force, and this reaction rate increases dramatically. Stars would burn through their fuel in geological eye blinks. The sun might live for millions rather than billions of years, insufficient time for the evolution of complex life. Moreover, the increased weak force would enhance neutrino production and interaction rates. Neutrinos, ghostly particles that barely interact with matter in our universe, would carry away energy more efficiently, cooling stellar cores and potentially preventing the supernova explosions that scatter heavy elements across space. Weaken the weak force, and proton fusion becomes even rarer. Stars burn more slowly, living longer but producing less energy. The delicate balance between gravitational collapse and fusion pressure might shift, creating stars that are dim and unstable. Moreover, the weak force governs the decay of free neutrons. In our universe, a free neutron decays into a proton, electron, and neutrino in about 15 minutes. Alter the weak force, and you alter this decay rate, which in turn affects the balance of protons and neutrons in the early universe. This balance determines the primordial abundance of helium. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion. Protons and neutrons fused into deuterium, then helium, creating the cosmic helium abundance we observe today, about 25% of all ordinary matter by mass. This precise percentage depends critically on the ratio of neutrons to protons at the time fusion began, which in turn depends on the weak force governing neutron decay. Alter the weak force, and the helium abundance changes. Too much helium, and stars burn differently, potentially preventing the formation of carbon and oxygen in sufficient quantities. Too little helium, and the nucleosynthesis of heavier elements might be suppressed. The weak force must be calibrated within a narrow range to produce a universe with the right mixture of elements for chemistry and life. These four forces, gravity, electromagnetism, the strong force, and the weak force, do not act in isolation. They interact in complex ways that determine the structure of matter from the smallest scales to the largest. But the forces alone are not sufficient to specify a universe. The matter upon which these forces act also possesses properties that must be finely tuned. Consider the electron, the tiny particle orbiting atomic nuclei. The electron has a mass approximately 1/2000th that of a proton. This ratio appears arbitrary, yet it proves critical for chemistry and life. If electrons were heavier, atoms would shrink because the heavier electrons would orbit closer to nuclei. Chemical bonds depend on electron orbitals overlapping in specific ways. Heavier electrons would alter these orbitals, changing chemical properties drastically. Molecules might fail to form, or form only flimsy structures unable to support the complexity required for life. Moreover, heavier electrons would affect stellar nucleosynthesis. In certain nuclear reactions, electrons get captured by protons inside nuclei, converting them to neutrons. If electrons were heavier, this process would occur more readily, altering the isotopic abundances of elements produced in stars. The precise mixture of stable isotopes that exists in our universe depends on electrons having exactly the mass they do. If electrons were lighter, different problems emerge. Lighter electrons orbit farther from nuclei, making atoms larger. Chemical bonds become weaker and longer. The proteins and DNA molecules essential for life might become too fragile to maintain their structures against thermal fluctuations. Moreover, lighter electrons would alter the energetics of beta decay and electron capture reactions, again disrupting the synthesis of heavy elements in stars. The electron's charge also matters profoundly. The electron carries exactly the opposite charge of a proton negative, where the proton is positive, equal in magnitude to incredible precision. This exact equality ensures that atoms are electrically neutral, with the positive charge of protons precisely cancelled by the negative charge of electrons. If this balance were violated even slightly, matter would carry a net electric charge, creating powerful repulsive forces between objects. Imagine if atoms had even a tiny net charge, just 1 part in a billion of the electron's charge. The electromagnetic repulsion between everyday objects would overwhelm gravity by enormous factors. You could not sit in a chair because the mutual repulsion between your body's atoms and the chair's atoms would blast you away. Planets could not hold together. The Earth would explode under its own self-repulsion. the universe would tear itself apart. The quarks that compose protons and neutrons also possess precisely calibrated masses. Quarks come in 6 varieties, or flavors, but only 2 types. Up quarks and down quarks comprise the ordinary matter around us. Protons contain 2 up quarks and 1 down quark. Neutrons contain 2 down quarks and 1 up quark. The down quark is slightly heavier than the up quark, and this small mass difference has enormous consequences. The mass difference between down quarks and up quarks, combined with the electromagnetic repulsion between protons, makes neutrons slightly heavier than protons. In our universe, a neutron weighs about 0.14% more than a proton. This tiny difference, less than 1 part per thousand, determines whether matter can exist in stable forms. If the down quark were lighter relative to the up quark, neutrons might become lighter than protons. This would invert the stability relationship between these particles. In our universe, free neutrons decay into protons because neutrons are heavier and can lose mass by transforming. But free protons are stable, unable to decay, because there exists no lighter nucleus into which they could transform while conserving energy and other quantum properties. Reverse this relationship, and protons would decay into neutrons. Atoms, which depend on stable protons in their nuclei, would disintegrate. Hydrogen, the most abundant element in the universe, would be unstable. All the hydrogen in existence would gradually transform into neutrons, which might themselves be unstable depending on the details of the mass relationships. The universe would be left with no stable atoms whatsoever. But the problem extends beyond simple stability. Even keeping neutrons heavier than protons, if we adjust the quark masses to change the neutron-proton mass difference, we alter nuclear physics profoundly. The binding energy of nuclei depends on the precise masses of protons and neutrons. If neutrons were significantly heavier, many nuclei that are stable in our universe would become unstable, capable of decaying by emitting neutrons or undergoing beta decay to reach more favorable configurations. Carbon 2, the stable isotope of carbon that forms the basis of organic chemistry, contains 6 protons and 6 neutrons. Its stability depends on a delicate balance of forces and binding energies. Make neutrons too heavy, and carbon-12 might decay, leaving the universe without the foundation for organic chemistry. Even if carbon-12 remains stable, other essential nuclei might not. Oxygen 1,6, nitrogen 1,4, iron 5,6. The specific isotopes of these elements that dominate in our universe exist in their observed abundances because of the precise mass relationship between protons and neutrons. Make neutrons lighter, approaching the mass of protons, and different isotopes become favorable. The early universe might have produced different ratios of elements. Stellar nucleosynthesis would follow altered pathways. The elements scattered by supernovae might not include the right mixture needed for rocky planets and organic chemistry. The mass of the neutron relative to the proton also affects the abundance of deuterium produced in the Big Bang. Deuterium-heavy hydrogen with 1 proton and 1 neutron forms a crucial stepping stone in stellar fusion reactions. The amount of deuterium produced in the primordial universe depends on how many neutrons were available when the universe cooled enough for fusion to occur. This, in turn, depends on the neutron decay rate, which depends on the neutron-proton mass difference. Too much deuterium, and it might burn away too quickly in stars, preventing the formation of heavier elements through certain reaction pathways. Too little deuterium, and stellar fusion might proceed too slowly or not at all in smaller stars. The precise abundance of deuterium we observe, about 26 atoms per million hydrogen atoms, represents another improbable calibration point, dependent on the quark masses being exactly what they are. Yet even with particles having the right masses and forces having the right strengths, the universe requires one more critical ingredient to support complexity: expansion at precisely the right rate. The universe has been expanding since the Big Bang, carrying galaxies away from each other as space itself stretches. The rate of this expansion is governed by the Hubble constant, but the long-term evolution of expansion depends on 2 competing factors: the density of matter and energy in the universe, which gravitationally decelerates expansion, and the mysterious dark energy, which accelerates expansion. In our universe, these factors are nearly balanced, producing an expansion rate that allows structures to form. In the early universe, matter dominated over dark energy, and gravity slowed expansion enough for matter to clump together under its own gravitational attraction. Regions slightly denser than average attracted more matter, growing denser still, eventually collapsing into galaxies and stars. This process required expansion to proceed slowly enough for gravity to overcome the tendency of expansion to pull matter apart. If the universe had expanded significantly faster in its early epochs, matter would have dispersed too quickly for gravitational collapse to occur. Tiny density fluctuations in the primordial plasma would have been stretched smooth before they could grow into galaxies. The universe would have remained forever homogeneous, a thin, expanding gas of hydrogen and helium, gradually cooling and diluting, never condensing into stars or galaxies. We can quantify this sensitivity. If the expansion rate immediately after the Big Bang had been larger by even 1 part in a million, the universe would have expanded too quickly for galaxy formation. 1 part in a million seems like a tiny change, but consider what it means. The expansion rate had to be calibrated to within 0.00001% of its actual value for structures to form. This is like throwing a dart from Los Angeles and hitting a specific millimeter on a target in New York. But the expansion rate also could not be too slow. If the universe had expanded more slowly, gravitational deceleration would have been stronger. The expansion might have reversed entirely, causing the universe to recollapse into a big crunch within thousands or millions of years, far too quickly for stars to form, let alone life to evolve. Even if the universe did not recollapse entirely, slower expansion would have allowed matter to clump together more strongly. Instead of forming discrete galaxies separated by vast voids, matter might have collapsed into supermassive black holes or into a few enormous galaxy clusters. The distribution of matter we observe galaxies of specific sizes, separated by specific distances, depends critically on the expansion rate being precisely calibrated. Today, the universe's expansion is accelerating due to dark energy, a mysterious component that exerts a repulsive gravitational effect. Dark energy constitutes about 70% of the total energy density of the universe. Its existence was discovered only in 1998 through observations of distant supernovae, and it remains one of the deepest mysteries in physics. The strength of dark energy is characterized by the cosmological constant, often denoted by the Greek letter lambda. This constant represents the energy density of the vacuum itself, the amount of energy contained in empty space. Quantum field theory, our best understanding of particle physics, predicts that the vacuum should have energy, but the predicted value exceeds the observed value by a staggering factor, 10 to the power of 120. This is not a typo. Quantum theory predicts a vacuum energy density 120 orders of magnitude larger than what we observe. This represents perhaps the worst prediction in the history of physics, a discrepancy so vast that it defies comprehension. If the cosmological constant had the value predicted by our particle physics theories, the universe would have expanded so rapidly that atoms could not form. Space would be ripping apart faster than light could traverse it. Yet the cosmological constant is not zero either. It has a tiny, but non-zero value, causing the accelerated expansion we observe today. Why is it so small compared to theoretical predictions, yet not exactly zero? This cosmological constant problem represents one of the greatest unsolved problems in theoretical physics. But here is the crucial point. If the cosmological constant were much larger than observed, still vastly smaller than the theoretical prediction, but perhaps 100 or 1,000 times larger than its actual value, the universe would have begun accelerating its expansion much earlier in cosmic history. This acceleration would have prevented galaxies from forming. The matter trying to collapse under gravity would have been pulled apart by the accelerating expansion of space itself. If the cosmological constant were negative instead of positive, it would cause space to contract rather than expand, creating an attractive force that would accelerate the universe's collapse. The universe might recollapse before stars could form, or at best might survive a few million years before crushing everything back into a singularity. The cosmological constant must be positive, but extraordinarily small, fine-tuned to 1 part in 10 to the power of 120 relative to its theoretical expectation for the universe to expand at the right rate to allow Galaxieformation, Stellerevolution, and the eventual emergence of life. Beyond expansion rate and vacuum energy, the universe required a specific distribution of matter to begin with. In the cosmic microwave background, the afterglow of the Big Bang that we can observe today, we see tiny temperature fluctuations that reflect density variations in the early universe. These fluctuations are extraordinarily small, varying by only about 1 part in 100,000 from the average temperature. This precise amplitude of fluctuations proves critical. If the primordial density variations had been larger, say 1 part in 10,000 rather than 1 part in 100,000, the clumping of matter would have been more extreme. Regions of slightly higher density would have collapsed more vigorously under gravity, forming black holes rather than stars. The universe might have been dominated by black holes early in its history, with little ordinary matter remaining to form galaxies as we know them. If the fluctuations had been smaller, 1 part in a million or less matter would have been distributed too uniformly. Gravity would have had insufficient seed fluctuations to amplify. Galaxies might have taken much longer to form, or might have been smaller and less tightly bound, potentially unable to retain heavy elements ejected by supernovae. The chemical enrichment of the cosmos might have proceeded too slowly for planets like Earth to form with sufficient heavy elements. The pattern of these fluctuations also matters. The cosmic microwave background shows fluctuations on all scales, from tiny patches covering small angles in the sky to large-scale variations spanning significant fractions of the observable universe. The power spectrum, describing the relative strength of fluctuations at different scales, has a specific shape that depends on numerous cosmological parameters. This shape determines the sizes of galaxies that form, the distribution of galaxy clusters, and the large-scale structure of the universe. It depends on the ratio of ordinary matter to dark matter, the total matter density, the expansion rate, and other parameters. Alter any of these, and the pattern of fluctuations changes, likely preventing the formation of the cosmic structure we observe. Dark matter itself presents another fine-tuning puzzle. Dark matter constitutes about 25% of the universe's total energy density, far more than the 5% contributed by ordinary matter. Dark matter does not interact with light, making it invisible, but it interacts gravitationally, and its presence is essential for galaxy formation. Computer simulations of galaxy formation reveal that without dark matter, galaxies would not form as we observe them. Ordinary matter alone cannot provide sufficient gravitational attraction to pull itself together into the rotating disk galaxies like our Milky Way. Dark matter forms gravitational scaffolding, creating potential wells into which ordinary matter falls, allowing galaxies to assemble. The ratio of dark matter to ordinary matter must fall within a specific range. Too much dark matter, and its gravitational influence would be so strong that ordinary matter would collapse into extremely dense structures, perhaps forming black holes instead of stars. Too little dark matter, and galaxies would be unable to form efficiently, or would be so diffuse that star formation rates would be suppressed. Moreover, dark matter must be cold, meaning its constituent particles must move slowly compared to the speed of light. If dark matter were hot, composed of fast-moving particles, these particles would stream out of small-scale density fluctuations, erasing them before they could collapse. Only large-scale structures could form in a hot dark matter universe, potentially producing a cosmos dominated by superclusters rather than individual galaxies. The properties of dark matter particles remain unknown, but whatever they are, these particles must have precisely calibrated masses and interaction rates. If dark matter particles interacted too strongly with themselves, they would clump together differently, perhaps forming dense cores at galaxy centers that would disrupt the motion of stars. If they interacted too weakly, they might not cluster efficiently enough to provide the gravitational scaffolding needed for galaxy formation. The nature of dark matter connects to the broader question of particle physics and the fundamental structure of matter. Our current understanding rests on the standard model of particle physics, which describes 3 generations of quarks and leptons force-carrying particles like photons and gluons, and the Higgs boson that gives particles mass. The Higgs boson was discovered in 2012 at the Large Hadron Collider, confirming a prediction made decades earlier. The Higgs field permeates all of space, and particles acquire mass by interacting with this field. The strength of this interaction determines the particle's mass. Electrons interact weakly with the Higgs field and have small mass. Top quarks interact strongly and have large mass. The Higgs field itself has an intrinsic strength, characterized by the vacuum expectation value, approximately 246 billion electron volts. This value determines the overall scale of particle masses in our universe. If the Higgs field were stronger, particles would be heavier. If weaker, particles would be lighter. The vacuum expectation value of the Higgs field represents another apparent fine-tuning. This value is not predicted by any fundamental principle we know. It appears to be a free parameter of nature. Yet, if it were significantly different, the consequences would cascade through all of physics. A stronger Higgs field would make quarks heavier, increasing the mass of protons and neutrons. Heavier protons and neutrons would bind together differently, altering nuclear physics. The fusion reactions powering stars would have different energy thresholds and reaction rates. Nucleosynthesis would follow different pathways, producing different abundances of elements. Moreover, heavier particles would affect the behavior of matter in the early universe. During the first microseconds after the Big Bang, quarks and gluons existed in a hot plasma before cooling enough to form protons and neutrons. The temperature at which this transition occurred depends on the masses of quarks, which depend on the Higgs field strength. Alter the Higgs field significantly, and you alter when and how protons and neutrons formed, potentially changing the primordial abundances of elements produced in Big Bang nucleosynthesis. A weaker Higgs field would make particles lighter, with opposite but equally profound consequences. Lighter quarks would form lighter protons and neutrons, changing nuclear binding energies and reaction rates. The chemistry of atoms would shift as electron orbitals adjusted to the altered nuclear masses. Beyond the Higgs field, the Standard Model contains numerous other parameters that appear arbitrary yet prove essential for the universe we observe. The strengths with which particles interact with different forces, the mixing angles governing how particles transform into one another, the masses of different particle species, all of these values must fall within narrow ranges for matter to behave as it does. Consider the top quark, the heaviest known elementary particle, with a mass about 173 times that of a proton. The top quark is so heavy that it decays almost instantaneously, existing for only about 10 to the power of -25 seconds before transforming into other particles. This extreme mass is peculiar, and physicists do not fully understand why the top quark is so much heavier than other quarks. Yet, the top quark's mass affects the stability of the Higgs field. Quantum calculations reveal that the Higgs field exists in a metastable state, stable for now, but potentially capable of decaying into a lower energy configuration if given sufficient energy. The top quark contributes to these quantum calculations because virtual top quarks constantly pop in and out of existence in the vacuum, affecting the Higgs field's properties. If the top quark were somewhat heavier, quantum corrections might destabilize the Higgs field entirely, causing it to collapse into a different vacuum state. Such a collapse would propagate through the universe at the speed of light, fundamentally altering the laws of physics everywhere it touched. All particles would acquire different masses. Atoms would rearrange or disintegrate. The universe as we know it would cease to exist. If the top quark were lighter, the Higgs field might be more stable, but the quantum corrections it provides would differ, potentially affecting other aspects of particle physics in unpredictable ways. The masses of other particles might shift slightly, which in turn could affect nuclear physics, chemistry, and the formation of complex structures. The existence of 3 generations of quarks and leptons also seems finely tuned. We have up and down quarks forming ordinary matter, but we also have charm and strange quarks in the 2nd generation and top and bottom quarks in the 3rd generation. Similarly, we have electrons, muons, and tau leptons. The heavier generations are unstable, decaying rapidly into lighter particles, and they play no direct role in the matter around us. Why do these heavier generations exist? They seem unnecessary for building atoms in chemistry, yet their existence affects particle physics in subtle ways. The mixing between different quark generations, described by the Kabibo-Kobayashi-Maskawa matrix, determines the rates of certain nuclear reactions and the degree of matter-antimatter asymmetry in the universe. This asymmetry is itself crucial and finely tuned. In the very early universe, matter and antimatter should have been created in equal amounts. When matter and antimatter meet, they annihilate, converting their mass into energy. If matter and antimatter had been exactly equal, they would have annihilated completely, leaving behind only radiation. No matter would remain to form atoms, stars, or galaxies. Yet, obviously, matter survived. There is a tiny asymmetry. For every billion antimatter particles in the early universe, there were 1,000,000,001 matter particles. After all the annihilation, only one particle in a billion remained, but this was enough. All the matter we observe today, every atom in every star and galaxy, represents that tiny excess. The origin of this matter-antimatter asymmetry remains uncertain, but it depends on specific conditions being met. Processes, violating baryon number conservation, charge parity violation, and departure from thermal equilibrium all must occur together. The Standard Model permits some of these processes, but not enough to account for the observed asymmetry. New physics beyond the Standard Model may be required. Whatever its origin, the matter-antimatter asymmetry must be precisely calibrated. Too much asymmetry, and the universe would contain too much matter. The denser early universe might have formed black holes instead of stars, or the increased matter density might have caused the universe to recollapse before galaxies could form. Too little asymmetry and insufficient matter would remain after annihilation. The universe might contain too few atoms to form galaxies, or the galaxies that did form would be so small and dilute that star formation would be suppressed. The chemistry of life requires not just atoms, but sufficient concentrations of atoms to form planets, atmospheres, and oceans. The relationship between matter, antimatter, and radiation energy in the early universe also determines the production of light elements through Big Bang nucleosynthesis. During the first few minutes of cosmic history, the universe was hot and dense enough for nuclear fusion. Protons and neutrons fused into deuterium, helium-3, helium-4, and trace amounts of lithium-7. The abundances of these primordial elements depend critically on the ratio of photons to baryons particles like protons and neutrons. In our universe, there are about 1,000,000,000 photons for every baryon. This ratio determines when fusion could begin. The universe had to cool enough that photons no longer had enough energy to blast apart newly formed nuclei, and how efficiently fusion proceeded. If there were fewer photons per baryon, the universe would have cooled more quickly during nucleosynthesis, potentially allowing more neutrons to survive and fuse into helium before decaying. The helium abundance might be higher, altering stellar evolution and nucleosynthesis in later generations of stars. If there were more photons per baryon, the universe would have remained hot longer, allowing more neutrons to decay before fusion could begin. Less helium would form, potentially affecting stellar evolution in the opposite direction. Moreover, the higher radiation pressure might have affected the growth of density fluctuations, altering galaxy formation. The specific abundances of primordial elements, about 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium, represent another precise calibration point. These abundances have been verified through observations of the oldest stars and the most distant gas clouds, confirming that Big Bang nucleosynthesis occurred as our theories predict. But the success of these predictions depends on dozens of finely tuned parameters having precisely the values they do. The neutron-proton mass difference, the weak force strength, the expansion rate during nucleosynthesis, the photon-to-baryon ratio, all must be calibrated within narrow ranges to produce the observed abundances. The formation of stars from primordial gas clouds represents yet another arena where precise calibration proves essential. After the Big Bang produced hydrogen and helium, these elements filled the expanding universe as diffuse gas. Gravity pulled this gas together into clumps, But for these clumps to collapse into stars required overcoming internal pressure generated by the thermal motion of gas particles. The Jeans mass, named after physicist James Jeans, specifies the minimum mass of a gas cloud that can overcome its own internal pressure and collapse under gravity. This critical mass depends on the temperature of the gas, its density, and the strength of gravity. In the early universe, the first gas clouds capable of collapsing had masses of perhaps 1,000,000 times the Sun's mass, forming the first generation of stars. These first stars, called population 3 stars, contained no heavy elements, only hydrogen and helium from the Big Bang. They were likely enormous, perhaps 100 to several hundred times the Sun's mass, burning incredibly hot and bright. They lived fast and died young, exploding as supernovae after only a few million years, and scattering the heavy elements forged in their cores across space. The existence and properties of these first stars depend on multiple fine-tuned parameters. The cooling rate of primordial gas determines how efficiently clouds can collapse. Gas must radiate away energy to collapse. If it cannot cool, thermal pressure prevents collapse. Hydrogen and helium have limited cooling mechanisms compared to heavier elements, which can radiate energy more efficiently through a variety of atomic transitions. If the cooling rate had been slower, primordial gas clouds might have been unable to collapse at all, or might have formed only extremely massive stars that exploded without producing the right mixture of heavy elements. If cooling had been faster, the first stars might have been smaller and longer-lived, delaying the chemical enrichment of the cosmos. The heavy elements produced by the first supernovae contaminated surrounding gas, enabling the formation of a second generation of stars, population 2 stars, that incorporated these elements. With each successive generation, gas clouds became more metal-rich, eventually producing population I stars like our Sun, which contains about 2% heavy elements by mass. This gradual chemical enrichment required billions of years of stellar evolution, with countless stars living and dying, each contributing heavy elements to the interstellar medium. The process had to proceed at the right rate, not too fast, lest all gas be locked into stars or black holes before planets could form. Not too slow, lest the universe expand and dilute before sufficient heavy elements accumulated. The specific mixture of elements produced by stellar nucleosynthesis depends on the detailed physics of nuclear reactions in stellar cores and supernova explosions. Different types of stars produce different elements. Low-mass stars, like red dwarfs, barely modify their composition, living for trillions of years, but contributing little to chemical enrichment. Medium-mass stars, like the Sun, produce carbon and nitrogen through the CNO cycle, scattering these elements when they shed their outer layers as planetary nebulae. Massive stars are the primary factories for heavy elements. In their cores, successive layers of fusion produce carbon, oxygen, neon, magnesium, silicon, and finally, iron. When the core becomes iron, fusion can no longer generate energy. Fusing iron consumes energy, rather than releasing it. The core collapses in a fraction of a second, then rebounds in a supernova explosion that tears the star apart. The supernova explosion itself creates elements heavier than iron through rapid neutron capture. Free neutrons, produced in the extreme conditions of the explosion, bombard iron and other nuclei, building up progressively heavier elements all the way to uranium and beyond. The specific abundances of these elements depend on the density of neutrons, the temperature, and the duration of the explosion, all of which depend on the star's mass, composition, and the fundamental forces governing nuclear reactions. If the strong nuclear force were slightly different, the binding energies of heavy nuclei would change, altering which isotopes are stable and which decay radioactively. Some elements might become impossible to produce. Others might be created in different abundances. The periodic table itself, the fundamental catalog of chemical elements, might be radically different. Consider carbon, the foundation of organic chemistry and life as we know it. Carbon is produced in the cores of red giant stars through the triple alpha process, where 3 helium nuclei fuse together. This reaction proceeds through an intermediate stage involving beryllium-8, an extremely unstable nucleus, that exists for only 10 to the power of negative 16 seconds before decaying back into helium. For the triple alpha process to work, a remarkable coincidence must occur. Carbon-12 has an excited energy level at 7.656 million electron volts, almost exactly matching the combined energy of beryllium-8 and a helium nucleus. This resonance dramatically enhances the reaction rate, allowing carbon to form in stellar cores before the beryllium-8 decays. If this energy level were slightly different, just 4% higher or lower, the resonance would not occur, and carbon production would be suppressed by factors of hundreds or thousands. The universe would contain far less carbon, potentially making carbon-based life impossible or extraordinarily rare. But the fine-tuning extends further. Oxygen-16 also has an excited energy level, positioned just barely below the energy threshold, that would create a similar resonance for converting carbon into oxygen. If this oxygen level were positioned slightly lower, the resonance would occur, and newly formed carbon would immediately fuse with helium to create oxygen. Stars would convert all their carbon into oxygen, leaving little carbon behind. The fact that carbon has a resonance perfectly positioned to enhance its production, while oxygen lacks a resonance that would destroy carbon, appears almost miraculous. The physicist Fred Hoyle, who worked out the details of stellar nucleosynthesis, found this coincidence so striking that it shook his atheistic convictions. The energy levels of carbon and oxygen seemed exquisitely calibrated to ensure that both elements could be produced in the quantities needed for life. This specific calibration depends on the strong nuclear force, the electromagnetic force, and the masses of quarks, determining proton and neutron properties. Alter any of these parameters even slightly, and the energy levels shift, potentially eliminating the carbon resonance or creating an unwanted oxygen resonance. Beyond carbon and oxygen, life requires numerous other elements. Nitrogen forms amino acids and nucleotides. Phosphorus creates the backbone of DNA and the energy currency of cells. Sulfur appears in some amino acids and many metabolic reactions. Iron sits at the active sites of many enzymes. Magnesium centers chlorophyll molecules. Calcium transmits signals in neurons and triggers muscle contractions. Each of these elements must be produced in stellar nucleosynthesis in appropriate abundances. The biochemistry of life uses elements roughly in proportion to their cosmic abundances. Carbon, hydrogen, oxygen, and nitrogen are both cosmically abundant and biochemically essential, while rare elements like gold play minimal biological roles. This correspondence cannot be coincidental. Life evolved using the elements available to it, but the fact that the elements required for complex chemistry happen to be among the most abundant heavy elements in the universe represents another remarkable calibration. If stellar nucleosynthesis produced different abundances, say, if iron were rare and gold were common, chemistry and biochemistry would be fundamentally different, if possible at all. The distribution of these elements across the galaxy also matters. Supernova explosions scatter heavy elements across space, but the elements must be mixed into gas clouds that will form new stars and planets. This mixing takes time and depends on galactic dynamics, the rotation of the galaxy, turbulence in the interstellar medium, and the rate of star formation. The Milky Way galaxy has been forming stars for more than 10 billion years, gradually enriching its gas with heavy elements. The Sun formed about 4.6 billion years ago from gas already enriched by previous generations of stars. This timing proved crucial. Earlier in galactic history, insufficient heavy elements existed to form rocky planets like Earth. Later, the star formation rate will decline as gas becomes depleted, making planetary systems rarer. Our solar system formed in a particular location within the galaxy, about 26,000 light-years from the galactic center, in a relatively quiet region between spiral arms. This location is significant. Closer to the galactic center, the density of stars is much higher, increasing the probability of close encounters that could disrupt planetary systems. Supernovae occur more frequently near the center, bathing nearby systems in sterilizing radiation. Farther from the galactic center, in the outer regions of the galaxy, heavy element abundances drop significantly. Planets forming in these regions contain less iron less silicon, less of all the elements needed to build rocky worlds. They might be smaller, less geologically active, less capable of maintaining the conditions necessary for life. Our position between spiral arms is also fortunate. Spiral arms are regions of enhanced star formation, where massive stars are born and die in rapid succession. Orbiting through a spiral arm periodically would expose a planetary system to increased supernova rates and higher radiation levels, potentially disrupting the long-term stability required for life to evolve. The orbit of the solar system around the galactic center takes about 230 million years a galactic year. This orbit is nearly circular, preventing the solar system from plunging into the dangerous inner regions or drifting into the metal-poor outer regions. Moreover, the solar system's orbital period is synchronized with the rotation pattern of the spiral arms in such a way that the Sun rarely enters the arms, spending most of its time in the safer inter-arm regions. This fortunate position in the galaxy depends on the initial conditions of the gas cloud that form the solar system, its position, velocity, and angular momentum. If the solar system had formed elsewhere in the galaxy, or with a different orbital configuration, the prospects for long-term planetary habitability might be diminished. Even the architecture of our solar system exhibits apparent fine-tuning. The planets orbit the Sun in a specific arrangement. Small, rocky planets close to the Sun, giant gas planets farther out. This configuration is not universal. Exoplanet surveys have revealed solar systems with giant planets orbiting extremely close to their stars, called hot Jupiters, and other exotic configurations. The presence of Jupiter in the outer solar system has profound effects on Earth. Jupiter's immense gravity influences the trajectories of comets and asteroids, either ejecting them from the solar system or altering their orbits. Computer simulations suggest that without Jupiter, Earth might be struck by large asteroids and comets far more frequently, with potentially devastating consequences for the development and persistence of life. Jupiter acts as a cosmic vacuum cleaner, protecting the inner solar system from bombardment. But Jupiter must be positioned correctly to perform this role. If Jupiter orbited closer to the Sun, its gravity might destabilize Earth's orbit. If Jupiter were more massive, it might cause even greater perturbations. If Jupiter were less massive or absent, the protection would be inadequate. The other giant planets, Saturn, Uranus, and Neptune, also contribute to the solar system's stability. Their gravitational interactions with each other and with Jupiter create a complex but stable dynamical configuration that has persisted for billions of years. Small changes in planetary masses, or orbital parameters, could destabilize this configuration, potentially ejecting planets from the solar system or causing them to collide. The formation of this particular planetary architecture depends on the properties of the protoplanetary disk from which the planets formed its mass, composition, temperature profile, and turbulence characteristics. These properties, in turn, depend on the conditions in the molecular cloud that collapse to form the solar system, which depend on the history of star formation and chemical enrichment in that region of the galaxy. Earth itself exhibits numerous apparently fine-tuned properties. Its mass is large enough to retain an atmosphere through gravity, but not so large that crushing surface gravity would prevent the existence of complex organisms. Its iron core generates a magnetic field that shields the surface from the solar wind and cosmic radiation, preserving the atmosphere and protecting life from harmful charged particles. The magnetic field depends on Earth having a liquid outer core surrounding a solid inner core. This configuration requires Earth to be the right size and composition, with sufficient radioactive elements in its interior to generate heat through decay. If Earth were smaller, it might have cooled more quickly, solidifying its core and shutting down the magnetic field. Mars, for instance, appears to have lost its magnetic field early in its history, allowing the solar wind to strip away much of its atmosphere. Earth's plate tectonics, the movement of crustal plates across the surface, plays crucial roles in maintaining habitability. Plate tectonics recycles carbon dioxide between the atmosphere and the Earth's interior, regulating greenhouse warming and keeping surface temperatures within the range where liquid water can exist. Without this carbon cycle, atmospheric carbon dioxide might accumulate to levels creating a runaway greenhouse effect, as occurred on Venus, or might be permanently locked in rocks, freezing the planet. Plate tectonics also drives volcanism, which releases gases from the interior to replenish the atmosphere and creates diverse landscapes from mountains to ocean basins. The chemistry occurring at mid-ocean ridges, where seawater circulates through hot rocks, may have been important for the origin of life, providing chemical energy and catalytic mineral surfaces. Not all rocky planets have plate tectonics. Venus and Mars apparently do not, though they may have in the distant past. Earth's plate tectonics depends on having the right amount of water enough to lubricate the motion of plates by weakening minerals and reducing friction, but not so much that the entire surface is covered by deep oceans with no exposed continents. The amount of water on Earth appears carefully calibrated. Earth's water probably came from asteroids and comets bombarding the young planet, with the total amount depending on the number and composition of these impactors, which depends on the architecture of the solar system and the timing of planet formation. Earth's orbit around the Sun places it squarely within the habitable zone, the range of distances where surface temperatures allow liquid water to exist. This zone is not a fixed region, but depends on the star's luminosity, the planet's atmospheric composition, and other factors. For the Sun, the habitable zone extends from roughly 0.95 to 1.37 astronomical units, with Earth at 1 astronomical units. Being in the habitable zone is necessary, but not sufficient for habitability. Mars is near the outer edge of the habitable zone, but is too small to retain a thick atmosphere and lacks plate tectonics to regulate its climate. Venus is near the inner edge, but suffered a runaway greenhouse effect, reaching surface temperatures hot enough to melt lead. Earth maintains its habitable climate through a combination of factors: the right distance from the Sun, the right atmospheric composition, plate tectonics regulating carbon dioxide, and a large moon stabilizing the axial tilt. The moon, Earth's natural satellite, is unusually large compared to the planet it orbits. Most moons in the solar system are tiny compared to their planets, but the moon has about 1/4 Earth's diameter and 1/80th its mass. This large mass ratio is exceptional and has important consequences. The moon's gravity stabilizes Earth's axial tilt, the angle between Earth's rotational axis and its orbital plane around the Sunday. This tilt, currently about 23.5 degrees, causes the seasons. Without the moon, Earth's axial tilt would vary chaotically over time due to gravitational perturbations from Jupiter and other planets. The tilt might range from 0 degrees, producing no seasons, to 85 degrees, creating extreme seasonal variations, with each hemisphere experiencing months of continuous daylight, followed by months of darkness. Such wild swings in axial tilt would cause dramatic climate instabilities, potentially making the long-term evolution of life more difficult. The moon's stabilizing influence keeps Earth's tilt varying only between about 22 and 24.5 degrees over tens of thousands of years, a gentle variation that contributes to glacial cycles, but does not threaten life's existence. The moon formed through a giant impact early in Earth's history, when a Mars-sized object struck the young Earth. The collision vaporized and ejected enormous amounts of material, which coalesced into orbit to form the moon. This impact was violent enough to have destroyed Earth if it had been significantly more energetic, yet gentle enough to leave behind a planet capable of supporting life. The probability of such an impact occurring with exactly the right energy, angle, and timing seems remarkably low. Too energetic, and Earth would be disrupted. Too gentle, and insufficient material would be ejected to form a large moon. If the impact had occurred later, after Earth cooled and differentiated, the resulting moon might have very different composition and size. The moon's presence also drives ocean tides through its gravitational pull on Earth's waters. These tides may have been important for the origin of life, creating tidal pools where organic molecules could concentrate and react. Tidal forces also transfer angular momentum from Earth's rotation to the moon's orbit, gradually slowing Earth's rotation and causing the moon to recede slowly from Earth. In the distant past, Earth rotated faster and the moon orbited closer, creating even stronger tides. Early Earth's day may have been only 6 to 8 hours long. The gradual slowing of Earth's rotation to its current 24-hour day occurred over billions of years, with the rate of energy dissipation depending on the configuration of continents and oceans, which affects how tidal energy is absorbed. The 24-hour day is itself significant for life. It allows for circadian rhythms matching the day-night cycle, enabling organisms to anticipate daily changes in light and temperature. If Earth rotated much faster, days would be very short, potentially preventing complex organisms from adapting properly. If Earth rotated much slower, days would be very long, creating extreme temperature swings between the sunlit and dark hemispheres. The Sun itself exhibits properties crucial for Earth's habitability. As a G-type main sequence star, the Sun burns hydrogen steadily, maintaining relatively constant luminosity over billions of years. This stability allows Earth's climate to remain within habitable bounds for the timescales required for life to evolve. Not all stars are so stable. Red dwarfs, the most common type of star, are smaller and cooler than the Sun, burning their fuel so slowly that they can live for trillions of years. This might seem ideal for life, but red dwarfs tend to be magnetically active, producing powerful flares that could strip away planetary atmospheres or sterilize surfaces with radiation. Moreover, planets must orbit very close to red dwarfs to receive adequate warmth, making them vulnerable to tidal locking and stellar activity. Larger, hotter stars than the Sun burn much more brightly, but live far shorter lives. An A-type star might live only a few 100 million years, on the main sequence insufficient time for complex life to evolve. Given that Earth required nearly 4 billion years to progress from single-celled organisms to complex animals, the Sun's position in this spectrum of stellar types, massive enough to live billions of years, stable enough to maintain steady luminosity, yet not so small that planetary habitability is compromised, represents another apparently fortunate circumstance. The Sun's metallicity, its content of elements heavier than hydrogen and helium, also matters. Stars with very low metallicity, formed early in galactic history, have fewer heavy elements to incorporate into planets. Their planetary systems, if they exist, might consist primarily of gas giants, with few or no rocky planets. The Sun's metallicity, of about 2% heavy elements by mass, represents enrichment from previous stellar generations, providing the raw materials for rocky planets. Yet, the Sun is not unusually metal-rich. Some stars have metallicities several times solar, which might seem beneficial for planet formation. However, very high metallicity stars tend to form more giant planets, which can migrate inward during planetary system formation, disrupting the formation of terrestrial planets or ejecting them from the system. The Sun's intermediate metallicity may be optimal for forming stable planetary systems with both terrestrial and giant planets in configurations conducive to long-term habitability. The galaxy, the solar system, the Earth, and even the Sun all exhibit properties that seem exquisitely calibrated for the existence of complex life. Stack these upon the fine-tuned fundamental constants and forces, and the improbability compounds to staggering levels. How do we make sense of this tower of improbabilities? How do we explain a universe so precisely calibrated that the slightest deviation in dozens of independent parameters would render it sterile and lifeless? Three major explanations have emerged from scientific and philosophical discourse, each with profound implications for our understanding of existence itself. The first explanation invokes the idea that the universe was deliberately crafted by an intelligent creator who set the fundamental constants and initial conditions with the specific intention of producing life. This theological perspective has ancient roots, but has been revitalized by discoveries in modern cosmology and physics. The argument from design, sometimes called the teleological argument, suggests that the exquisite fine-tuning we observe constitutes evidence of purposeful creation, much as the intricate mechanisms of a watch imply the existence of a watchmaker. Proponents of this view argue that the sheer number of independent parameters requiring precise calibration exceeds what chance could plausibly explain. They point to the apparent goal-directed nature of the universe's structure, how atomic physics permits chemistry, how chemistry permits biology, how biology permits consciousness. Each level builds upon the previous one in ways that seem intentional, as if the universe were designed from the ground up to support complex, self-aware beings capable of contemplating their own existence. The design hypothesis faces several challenges from a scientific perspective. Science operates by proposing testable hypotheses about natural phenomena, seeking explanations in terms of physical laws and mechanisms. Invoking a supernatural designer places the explanation outside the realm of empirical investigation. We cannot test the designer hypothesis experimentally, cannot make predictions about what a designed universe should look like beyond the observation that it should be compatible with our existence. Moreover, the design hypothesis raises as many questions as it answers. If the universe requires a designer to explain its fine-tuning, what explains the designer? If complex, fine-tuned systems require intelligent creators, then surely a being capable of designing an entire universe must be extraordinarily complex and finely tuned itself. Who designed the designer? This leads to an infinite regress, unless we arbitrarily declare that the designer needs no explanation, which undermines the original argument that fine-tuned complexity requires explanation through design. Critics also note that invoking design prematurely may discourage the search for deeper physical explanations. Throughout history, phenomena once attributed to divine intervention, lightning, disease, planetary motion have yielded to natural explanations as scientific understanding advanced. The fine-tuning of the universe may likewise admit of a natural explanation that we have not yet discovered. The second major explanation appeals to the anthropic principle, often combined with the multiverse hypothesis. The anthropic principle, in its weak form, observes that we should not be surprised to find ourselves in a universe compatible with our existence. We could not possibly observe a universe incompatible with observers like us. This seems almost tautological, yet it has explanatory power when combined with the multiverse idea. The multiverse hypothesis proposes that our universe is not unique, but rather one among a vast ensemble of universes, possibly infinite in number. These universes might have different values for their fundamental constants, different laws of physics, different initial conditions. Most of these universes would be sterile, incapable of supporting stars, planets, or life. But given a sufficiently large multiverse, some universes, however rare, would happen to have the right parameters for complexity and life to emerge. We necessarily find ourselves in one of these rare, habitable universes simply because we could not exist in the sterile ones. The fine-tuning is explained not by design, but by observer selection bias. Just as we should not be surprised to find ourselves on Earth rather than on barren Mars or Venus, because we could only evolve on a habitable planet, we should not be surprised to find ourselves in a life-permitting universe, rather than a sterilely one. Several theoretical frameworks in modern physics lend support to the multiverse idea. Eternal inflation, a variant of the inflationary cosmology that explains the universe's large-scale uniformity, suggests that quantum fluctuations in the inflating field create bubble universes continuously. Each bubble universe might have different properties, determined by how the fundamental field settled into their lowest energy states as that universe cooled. String theory, which attempts to unify quantum mechanics and general relativity by modeling fundamental particles as tiny vibrating strings, predicts an enormous landscape of possible vacuum states, perhaps 10 to the power of 500 different configurations, each corresponding to a universe with different physical laws. If all these possible universes actually exist somewhere in a vast multiverse, then ours is simply one among countless variants, distinguished only by the fact that its particular configuration permits our existence. The multiverse hypothesis has the advantage of potentially explaining fine-tuning without invoking supernatural intervention. It operates entirely within naturalistic frameworks, albeit frameworks that extend far beyond what we can directly observe. It also addresses the problem of improbability. Given infinitely many universes with randomly varying parameters, even the most improbable configurations must occur somewhere. However, the multiverse hypothesis faces serious criticisms. Most fundamentally, it may be untestable. If other universes exist beyond the observable horizon of our own, causally disconnected from us, then we cannot observe them, visit them, or conduct experiments to verify their existence. Science relies on empirical verification, but a multiverse lying forever beyond our observational reach cannot be confirmed or falsified through observation. Some physicists argue that the multiverse hypothesis is not truly scientific, but rather metaphysical speculation dressed in the language of physics. Others counter that we can test the theories that predict multiverses inflation and string theory, and if these theories prove correct, we should accept their implications even if those implications include unobservable entities, just as we accept the existence of quarks, despite never observing them in isolation. The multiverse also raises subtle issues of probability and prediction. If infinitely many universes exist with all possible variations of physical constants, then anything that can happen does happen somewhere. This makes it difficult to make meaningful predictions. Why should our universe have the specific fine-tuning values it does, rather than some other set of life-permitting values? The multiverse hypothesis explains why some universe has life-permitting values but struggles to explain the specific values we observe. Additionally, some critics argue that the multiverse explanation sacrifices explanatory parsimony. Occam's razor suggests we should prefer simpler explanations over more complex ones. Invoking an infinite ensemble of unobservable universes to explain the properties of the one universe we can observe might be considered extravagant. Defenders respond that the multiverse follows naturally from well-motivated physical theories, rather than being arbitrarily posited to solve the fine-tuning problem. The third approach suggests that we remain ignorant of deeper physical principles that will eventually explain why the fundamental constants must have the values they do. Perhaps the apparent fine-tuning reflects our incomplete understanding of physics. A more fundamental theory might reveal that the constants we treat as independent and arbitrary are actually interrelated through deeper laws, constrained to their observed values by logical necessity. This perspective maintains that the universe's properties are not contingent, not arbitrary values that could have been different, but necessary consequences of deep physical principles we have not yet discovered. Just as the speed of light in vacuum and the strength of the electromagnetic force seem like independent constants, but are actually related through the fine structure constant, perhaps all fundamental parameters are interrelated through some master equation or principle. Historical precedent supports this possibility. Kepler's laws of planetary motion initially appeared to be arbitrary, empirical relationships, describing how planets happen to move. Newton's theory of gravitation revealed these laws as necessary consequences of the inverse square law of gravity and the principle of inertia. Similarly, the periodic table of elements once seemed like an arbitrary catalog of chemical substances until quantum mechanics explained it as a necessary consequence of atomic structure and the Pauli exclusion principle. Could a future theory of everything, perhaps a final formulation of string theory, or loop quantum gravity, or some framework we have not yet imagined, reveal that the fundamental constants could not possibly have any values other than those we observe? Might such a theory show that universes with different parameters are not merely improbable, but literally impossible, violating deep, logical, or mathematical principles? Some physicists and mathematicians have explored whether purely mathematical considerations might constrain physical laws. The physicist, Max Tegmark, has proposed that the universe is fundamentally mathematical, that physical reality simply is a mathematical structure. Under this view, the laws of physics are not arbitrary rules imposed on a pre-existing reality, but rather properties inherent in the mathematical structure that constitutes reality. Perhaps only certain mathematical structures are logically consistent, and the apparent fine-tuning reflects constraints arising from mathematical necessity. Others have suggested that principles of quantum gravity or holography might constrain the possible values of constants. The holographic principle, derived from studies of black hole thermodynamics, suggests that the information content of any region of space is encoded on its boundary surface, with profound implications for the structure of space-time and quantum field theory. A complete theory of quantum gravity incorporating holographic principles might reveal constraints on fundamental parameters that we cannot yet perceive. The difficulty with this approach is that it remains largely speculative. We do not currently possess a complete theory of everything that successfully explains why the constants have their observed values. String theory, the most developed candidate, has not yet produced definite predictions for particle masses and coupling constants. Loop quantum gravity focuses primarily on space-time structure rather than particle physics. No existing framework has demonstrated that the fundamental constants are uniquely determined by deeper principles. Moreover, even if a theory of everything eventually emerges, it may simply reveal new layers of apparent fine-tuning at deeper levels. The theory itself might contain free parameters, or initial conditions that require explanation. We might find ourselves asking why the master equation has the form it does rather than some alternative form. The question of why anything exists at all, and why it exists with the particular logical structure it possesses, may lie forever beyond scientific explanation. Some philosophers argue that this regress is inevitable, that science can explain how the universe operates and even how it began, but cannot ultimately explain why the laws of nature are what they are, rather than something else. The most fundamental layer of explanation might necessarily involve brute facts, facts that simply are, without deeper explanation. Whether we accept a multiverse, a designer, or necessary physical principles as the stopping point for our explanatory chain, we eventually encounter something that cannot be explained in terms of anything more fundamental. Yet the search for deeper understanding continues. Physicists pursue unified theories that might explain the fundamental forces in particles. Cosmologists probe the earliest moments of the universe, seeking clues about initial conditions and the mechanism of cosmic inflation. Astronomers search for life beyond Earth, testing whether the emergence of biology requires the same fine-tuning that permits our existence, or whether life might arise under a wider range of conditions than we imagine. The discovery of extraterrestrial life, particularly intelligent life, would provide valuable data for assessing fine-tuning arguments. If life proves common in the universe, arising readily wherever conditions permit, it might suggest that the requirements for biology are less stringent than currently believed, potentially weakening fine-tuning arguments. Conversely, if decades or centuries of searching reveal that Earth harbors the only life in the observable universe, this would strengthen the claim that life requires extraordinarily precise conditions. The search for life also extends to understanding the origin of life on Earth. How did non-living chemistry transition to living biology? What minimum conditions are necessary for this transition? If life originated through processes that require only generic chemical properties, properties that would exist under a wide range of possible physical laws, then perhaps the fine-tuning of physics for life is less remarkable than it appears. But if the origin of life required very specific molecular structures that depend critically on precise atomic properties, this would reinforce fine-tuning arguments. Laboratory experiments attempting to recreate the origin of life have made progress in understanding how simple organic molecules might form and combine under early Earth conditions. Researchers have synthesized amino acids, nucleotides, and lipid membranes using plausible prebiotic chemistry. Yet the gap between simple organic molecules and self-replicating, evolving systems remains vast. No one has yet created artificial life from non-living components, and the mechanisms by which this transition occurred naturally remain uncertain. Some researchers suggest that the origin of life might be a nearly inevitable consequence of chemistry under the right conditions, implying that life should be common throughout the universe. Others argue that the transition to life required multiple improbable events occurring in sequence, making the origin of life rare even on habitable planets. The resolution of this question will significantly impact our assessment of cosmic fine-tuning. The fine-tuning question also connects to the nature of consciousness, and whether it requires special physical conditions beyond those needed for life generally. If consciousness emerges naturally from sufficiently complex information processing systems, then any universe permitting chemistry and evolution might eventually produce conscious observers. But if consciousness requires very specific neural architectures or quantum processes in the brain, then the requirements for conscious life might be even more stringent than those for simple biology. Some philosophers and scientists have proposed that consciousness itself might be a fundamental feature of reality rather than an emergent property of complex matter. Panpsychism, the view that consciousness or proto-consciousness exists at all levels of reality, would imply that the universe is not fine-tuned for consciousness, but rather that consciousness is intrinsic to physical systems. This perspective remains controversial and difficult to test empirically, but it represents one attempt to address the puzzle of how subjective experience arises from objective physical processes. The hard problem of consciousness explaining why and how physical processes give rise to subjective experience remains unsolved. We can describe neural correlates of consciousness, mapping which brain regions activate during different mental states, but we cannot explain why these physical processes feel like anything from the inside. Some argue that this explanatory gap indicates a fundamental limitation in our materialist framework, suggesting that consciousness might require new physics or even a dualistic framework separating mind from matter. If consciousness does require special physical conditions or new physics beyond the standard model, this would add another layer to fine-tuning arguments. The universe would need to be fine-tuned not only for stars, atoms, and chemistry, but also for the specific conditions that permit subjective experience. Conversely, if consciousness emerges naturally from any sufficiently complex information processing system, then the apparent fine-tuning for consciousness reduces to fine-tuning for complexity generally. These profound questions about existence, consciousness, and cosmic purpose have motivated thinkers for millennia, but modern physics has transformed the discussion by quantifying the degree of apparent fine-tuning with mathematical precision. Ancient philosophers could speculate about whether the universe was designed or arose by chance, but they lacked the detailed knowledge of physical laws that would allow them to calculate just how improbable our universe appears to be. Now we can enumerate the constants, measure their values, and calculate what would happen if they differed even slightly. We can run computer simulations of stellar evolution, nucleosynthesis, and galaxy formation under different physical laws. We can quantify the degree to which multiple independent parameters must be calibrated within narrow ranges to permit complexity and life. This quantification does not resolve the debate between design, multiverse, and physical necessity explanations, but it sharpens the question and constrains possible answers. We now know with considerable precision just how special our universe appears to be, just how narrow the habitable range of parameters seems to be for most fundamental constants. The resolution of this question, if it comes at all, may emerge from unexpected directions. A breakthrough in quantum gravity might reveal new constraints on physical laws. The detection of gravitational waves from the Big Bang might provide evidence for or against eternal inflation and the multiverse. A theory of everything might successfully predict particle masses and coupling constants, demonstrating their mathematical necessity. Or we might discover that our current understanding is fundamentally incomplete in ways we cannot yet imagine. Meanwhile, the fine-tuning of the universe for life stands as one of the deepest mysteries in science. Whether we interpret it as evidence for design, as an artifact of observer selection in a multiverse, or as a hint of deeper physical principles awaiting discovery, the fact remains. The universe is balanced on a knife edge of possibility, its very existence dependent on the precise calibration of dozens of independent parameters. We find ourselves in a cosmos exquisitely suited to our existence, a cosmos where the forces binding quarks into protons have exactly the right strength, where stellar cores fuse precisely the right mixture of elements, where planets orbit at exactly the right distances from their stars. We inhabit a universe where carbon has a resonance at precisely the energy needed for its production, where the cosmological constant is positive but vanishingly small, where the neutron is just slightly heavier than the proton. Change any of these parameters, even infinitesimally, and the universe collapses into sterility, a dark void of scattered hydrogen, or a blazing inferno of radiation, or a fleeting flash that reclapses into nothingness before stars can form. Our universe, against all odds, threads the needle through this gauntlet of impossibilities, permitting matter, energy, structure, chemistry, life, and consciousness to emerge from the quantum foam of the Big Bang. Whether this represents the handiwork of an intelligent designer, a statistical inevitability in an infinite multiverse, or a necessary consequence of deep physical principles remains unknown. The question may lie at the boundary of what science can answer, touching on issues of existence, purpose, and meaning that have preoccupied philosophers and theologians throughout human history. What we can say with certainty is that the universe is profoundly improbable, or at least appears profoundly improbable, given our current understanding. Every atom in your body, every photon illuminating your vision, every electrical impulse firing in your neurons exists because the universe possesses a very specific set of properties that seem extraordinarily unlikely to have arisen by pure chance. You are made of stardust, quite literally. The carbon, nitrogen, oxygen, and other elements comprising your body were forged in the cores of ancient stars and scattered across space when those stars exploded. Those stars burned because nuclear forces had precisely the right strength to permit fusion. Those elements combined into complex molecules because electromagnetic forces had precisely the right strength to permit chemistry. Those molecules organized into living cells because the laws of thermodynamics permit local decreases in entropy at the expense of larger increases elsewhere. The chain of improbabilities extends from the quantum scale to the cosmic scale, from the first moments of the Big Bang to the present day, from the fundamental constants of nature to the specific configuration of our solar system. At every level, the universe had to be precisely calibrated for you to exist, for life to exist, for complexity of any kind to exist. Some find in this realization a sense of profound purpose, evidence that the universe was meant to produce conscious beings capable of understanding it. Others find cosmic humility, recognizing our existence as a vanishingly rare occurrence in an unimaginably vast ensemble of possible universes. Still, others see an invitation to deeper understanding, a challenge to uncover the hidden principles that might explain why the universe must be exactly as it is. The question remains open, one of the greatest mysteries confronting science and philosophy. Why is the universe so perfect for our existence? Could it have been created by design? Or are we simply the beneficiaries of a cosmic lottery? Or does some deeper truth await discovery that will reveal the apparent fine-tuning as an inevitable consequence of logic and mathematics? We stand at a unique moment in human history, equipped with instruments and theories capable of probing the deepest mysteries of existence, yet still fundamentally uncertain about the ultimate nature and origin of reality. The universe has revealed many of its secrets, but the most profound question, why it exists at all, and why it exists with the particular properties it possesses, remains tantalizingly beyond our grasp. Perhaps future generations will solve this mystery, discovering the theory of everything that explains the fundamental constants, or confirming the multiverse hypothesis through some ingenious experiment. Perhaps the question will prove forever unanswerable, a permanent mystery at the foundation of existence. Or perhaps the answer will come from an entirely unexpected direction, transforming our understanding in ways we cannot currently imagine. For now, we can only marvel at the universe's exquisite calibration, contemplate the tower of improbabilities upon which our existence rests, and continue the search for deeper understanding. We can observe the cosmos with wonder, recognizing that we are conscious arrangements of matter capable of contemplating the very laws that brought us into being. The universe is vast, beyond comprehension, ancient beyond measure, and governed by mathematical laws of extraordinary precision. Whether this represents intentional design, random chance filtered through observer selection, or necessary consequence of deeper principles, it commands our attention and our awe. We exist because the universe permits existence. We question because the universe permits consciousness. We search for answers because the universe permits inquiry. And in that search, in that capacity for wonder and understanding, perhaps we glimpse something profound about the nature of existence itself, that a universe capable of producing beings who can ask why they exist is somehow more remarkable, more meaningful than one that simply exists without awareness of itself. Whether by design, by chance, or by necessity, we find ourselves in a cosmos that has become conscious of itself through us. The answer to why the universe is so perfect may ultimately matter less than the fact that we can ask the question at all. In a universe that could so easily have been sterile and dead, we live, we think, we wonder. That alone is extraordinary.